It's great to be here at this exciting meeting of a whole new exciting field of physics and astronomy. And I'm going to talk about why I think this is such an incredibly interesting experiment. Okay, so let me start with what I consider the best picture ever, which is this picture that the EHT took. I cried when I saw this picture. I'd been thinking about black holes for 30 or 40 years, and there was some nagging doubt that they really existed, and that all went away. Now, so this is a very exciting picture, incredible tour de force of by the astronomers and astrophysicists. Um, And it's very strong evidence, or I'd say overwhelming evidence for a black hole. But of course, we don't actually see the black hole. The black hole is sitting in that it's not emitting any light, um, and it's sitting in the middle there. And so, what can we actually learn about the black hole from this picture? And other than it's there. And so I think very shortly after this picture was taken, um, there was a question of if we take better pictures, which we want to do, what can we actually learn about the black hole, the curvature of space-time, as opposed to the also very interesting um, structure of the magnetosphere and the accretion disk and all that. But underlying this picture, there's a curved space-time which has a structure that was very precisely predicted by the Einstein equations more than a century ago. How can we learn about that? What can we learn about black hole from studying this image or getting better images? And this is the kind of sharp questions that theoretical physicists love. Very well posed, and also the kind of question they can almost never answer. Um, but surprisingly, in this case, there there is a very sharp answer with a rich structure which probes the essence of space-time curvature and Einstein's theory of general relativity. And that's already very wonderful for thing. But even more amazingly, it seems to be just barely within the the measurement of these predictions appeared just barely um, within the reach of current space-based technology. And um, and that was explained in this paper. And for the first couple of years after we wrote this paper, I kind of thought, well, yeah, this is too good to be true. Um, Something is gonna, we won't be able to beam down enough information, uh, or we won't be able to get a cold enough refrigerator or big enough antenna, or it'll be, you know, um, you know, $10 billion instead of, a couple hundred million or something. But as time went on, all the deal breakers seem to potential deal breakers seem to evaporate, and this is something that I feel like all the ducks lined up in the right way. This project had really good karma, and so why is it possible um, to to see this? I mean, space-time curvature is a very subtle thing. How can we do measurements on Earth that can probe this in a very precise way, or not quite on Earth, but near Earth? And ultimately, the answer has to do with the symmetry of the geometry of a black hole that we did not know about when we started this project. And symmetries are a very powerful tool in physics, and symmetries can emerge under certain circumstances, and not so much so far in astronomy. I hope there's more of this in the future of astronomy. Actually, symmetries do come into studies of the uh, early universe and the CMB, but they are very useful in condensed matter physics for organizing and interpreting the many complex phenomena that can be measured. And of course, condensed matter, or the study of materials, is a much older subject. And it wasn't true at the beginning that the power of symmetries was understood. And one of the most ubiquitous symmetries, a conformal symmetry, emerges outside the ring, outside a black hole, and this is the photon ring. But let me back up and say, what is conformal symmetry? There it is. So conformal symmetry, a system has conformal symmetry if, as you zoom in on it, the harder you look, the more it looks the same. And this is not a symmetry like boost or rotational symmetry in our universe, but it can emerge under certain circumstances. One of the first examples of this was critical opalescence in the carbon dioxide liquid gas transition, which occurs at certain critical temperature and pressure. And what happens is if you're right at the phase transition where liquid is about to turn into a gas, the dynamics of the system, it's not true. You can't see it by looking at the equations that govern uh, the individual molecules, but at the critical temperature, there's a collective, the behavior is dominated by collective modes, and they have wavelengths. The critical theory at the phase transition has a conformal symmetry, and the conformal symmetry says that all wavelengths are equally good, and so if you send light at it, um, it can absorb, light can be absorbed at any wavelength. So if you're sitting there with a light bulb looking at it and you hit the critical point, all of a sudden the light will disappear. That's the critical opalescence. So this is typical of whenever you have asymmetry in nature, there's something really weird that suddenly becomes visible. And so symmetries often lead to very striking, observable, experimentally observable phenomena. And that is what happens um, in black holes. Now, the symmetry we're talking about is when you approach the photon ring, but about 20 years ago, it was understood, actually, sorry, 30 years ago, it was understood that black holes, under certain circumstances, including Kerr black holes, have this symmetry. If you imagine that picture, they have that symmetry literally as you approach their horizon. So that was the kind of inroad for this conformal symmetry that's such a powerful tool in condensed matter physics to make its way into astrophysics. But it was understood theoretically, and it became very important. I'm just going to have one slide on this in understanding what's called the black hole information puzzle. So according to Einstein and Schwarzschild, black holes, unlike stars, which are described by many, you know, uh, the magnetosphere, the rotation, the individual motion of all the chemical composition. They have many parameters describing, and every star is very different, but all black holes are the same. once the thing collapses, it's it goes into a unique state. Now, Stephen Hawking, um, about 50 years ago, you put quantum mechanics in the picture, and he showed that black holes radiate. And from that, he used the thermodynamic reasoning to infer that not only do they have many internal characteristics, but they are actually the most complex thing in the universe. They're the best hard drives that one can possibly make. So we had two different pictures of black holes, and we couldn't understand how to reconcile them. And so what was done um, was in special kinds of black holes in string theory, we could completely tear the black hole apart theoretically, find a description that got all the states, all the bits, the qubits or of the black hole, and we could count them. And to count them, we had to use the conformal symmetry. And it was the same conformal symmetry, or that was the only way that we could find to count them. And we used the conformal symmetry, and that reconciled this picture between simplicity and complexity of black holes. Okay, so now um, there's another kind of conformal symmetry, the one that occurs near the photon ring. And let me now describe um, how that happens. So this is a picture on the Beck's website, if you haven't already seen it. And in the middle is a black hole. Space-time is curved, and we shoot light passes by, and it hits the screen, and that's the image that we saw. Now, we can also have photons which orbit once, and they are focused into a ring. And they can only, they have to hit the black hole at just the right distance in order to uh, orbit like that. They have to go near the photon ring. And so we get not one, but we get a series of concentric rings around the black hole. So, so how does this work? So if we look at the where is the conformal symmetry here? So if we look at the large blue person at the left, that is supposed to be the direct image. Then over um, on the lower right corner, we would also see, so in the middle is a black hole, and over in the far right corner, we have an image from a photon which went around the back of the black hole and back of the black hole and came back up. And we can see that that image, however, is both inverted and stretched. Now, what I'm calling the n equals 2 image there, you would start with a photon that was heading toward us, but got waylaid by the black hole, made one full orbit, and then came back. And similarly, we have an n equals 3 image and an n equals 4 image. This is all and all these images converge on the yellow-orange circle in the middle, which is the photon ring. And similarly, if there's someone inside the black hole, their image can arrive at the telescope in a variety of different ways that depend on how many times they orbit the black hole. And there's a very bright ring of light that will appear at the locus of the place where the photons can actually orbit the black hole. Now, these, well, I'll talk about that a little later. No, maybe I'll talk about it here. So, what we hope to see in Beck's is only the n equals one ring, which is the the one on the lower right corner, because if you want to see the subsequent rings, um, you need that each ring is more stretched and thinner and has less net luminosity. And to see the subsequent rings, you have to go to higher orbit. So that's one of the nice things for all of you entering this field. If Bex is successful, which I'm confident it's going to be, it's just the beginning. So there's going to be a century of ever more exciting experiments going to higher and higher orbits and um, probing the black hole with um, more and more sensitivity. So, for example, the n equals 2 ring, that will be the moon mission, and the n equals 3 ring, the n equals 3 ring will be L2. So, this is not a one-off thing. I think it could have a run as long as, I think accelerators have kind of come to the end of their useful life. So this is like working on Bex is being like uh, building the first bubble chamber accelerator at the LBL Lawrence Berkeley Laboratory, whatever that was, 75 years ago, I guess. Um, so it's a field with a great future. Okay, so these successive images, what I've been talking about conformal symmetry, these successive images or rings are related by conformal symmetry, as Alex and Shahar and I uh, showed. And this symmetry actually acts on the geometry of the black hole, and it's it's closely related to the symmetry that we use to resolve the quantum puzzles of black holes. So, saying conformal symmetry to a quantum gravity person who works on black holes is like waving red meat in front of a dog. So people get very excited about this. And so there's, people interested in understanding. I mean, the main thing is, of course, is the mission to build this thing and see it. But this thing the photon ring could conceptually have important implications for the many, many things. So I should stress there are many things that we don't understand about black holes. They're the least understood objects in the universe. And Bex is about the observation of them, but there's also a big theoretical program trying to understand um, what, you know, what's inside them, and particularly the quantum story. So it's it's very exciting that these experimental and theoretical efforts are at least starting to touch each other. And certainly my own interaction with the astronomers and astrophysicists has stimulated me to ask different questions and think about things in new ways um, that are that have been very productive. So meanwhile, how are we going to see this thing? Well, the EHT already used up the whole Earth just to had to wire the whole Earth into a giant telescope in order to see the black blob in the middle. And now we find we need not that much, but kind of an order of magnitude, maybe less than an order of magnitude, better resolution, but still we got to get off the Earth. Um, and so that brings us to the Black Hole Explorer. So have another, um, we need to have another telescope up in the sky, and that needs to coordinate with the ones on the Earth. And that, of course, is what you just heard about from Michael, and we'll hear much more about the the det how this is going to happen in the rest of this meeting. Um, I guess I've uh, went a little fast, but thank you. I hope there's some questions.
Thanks so much, Andy. That was terrific. Questions for Andy? Well, maybe I'll kick things off as people are warming up. But I love your description of Bex as the bubble chamber equivalent, sort of launching a century of progress in studies of black holes. I'm really curious. Astronomers, we're all butterfly collectors. We like lots of things. And I'm curious for your view in this sort of century-long time scale of, is one black hole enough? Are they all, one tells you everything you want and you just want to study it intensively? Or what is the role of trying to expand the source size for Bex in this, from the perspective of theoretical physics and holography? What would be the prioritization there?
Well, yeah. So the statement about butterfly collectors is really interesting, and it's been interesting to me talking to you and to many other astronomers that I've Ramesh and Shep and at the BHI. It's really interesting the difference. And I also talk to a lot to mathematicians over a lot of my career, and it's really different. It's really interesting how different subjects in science have very different ideas about what's interesting, what constitutes progress, and and you know and it's I think there isn't a definite answer to the question, what is scientific progress? So, in my interactions with mathematicians, you know, there's a bit of nothing is interesting unless you can prove it completely rigorously. And in interactions with astronomers, there's a sense of the only thing that okay, I've talked a lot of, maybe I'm getting myself in trouble here, but they're interested in what you can see. It's that's the goal, to just to see more and um, less emphasis on, general a general understanding. And I think it is fair to say that, experimental uh, physics is a much older subject than than astronomy. Of course, the ancient Greeks but there was a limited amount of data and that they could obtain. And in the beginning of the 18th century, physics was about, you had a shelf full of compounds and you took them off the shelf and you added, you measured their thermodynamic properties, and it wasn't the idea that there should be unifying themes and organizing principles was there. Of course, Newton organized some things, but it wasn't quite as prevalent as it is now. And in particular, the idea of symmetry. That the idea that symmetry was a powerful organizing principle, is really only the last 100 years and 150 years. So, so I think that that I hope I think it would be useful to have more of that in in astronomy. Um, and Yeah, I do think though now we're going to, be able to see the sky in the kind of detail that we never had before. So there's going to be enough data that that
Yeah.
we can organize things in a different way. And by the way, I didn't mention this, but also the scale invariance of the CMB spectrum and the deviations from it are all related to a conformal symmetry. That's another example of a conformal symmetry. And in inflation, the whole universe looked the same as you looked at it um, on different time scales. And as far as whether we need to look at more black holes, yes, looking at more black holes is good, but in the case of this, what we need to understand the symmetry is more rings. And those are already sitting there around M87. But of course, more black holes is always good. Yeah.
Yeah. Okay, Elliot, go for it.
I think you just sort of answered the question I was going to ask, which was on this multi-decade perspective, what is the role you see of what we will learn from the n=1 ring, what we will learn from the n=2 ring, what we will learn if we ever could see the n=3 ring, et cetera? I mean, I'm just curious to get a sense of what
Yeah.
information one gains
Yeah.
yep, thanks.
Yeah. So, of course, you know, um, um, what we the thing that is really does not involve any astrophysics whatsoever, just general relativity, is the ratios of quantities on successive rings. So if you're, um, so for example, and so if you look at like the first photon ring and you compare the luminosity at a certain angle and the polarization at a certain angle to the one on the first on the second, and those are related by critical exponents of the Kerr geometry. And so basically the collection of all the successive rings are just a repackaging, and they contain all the information about the geometry. It's not as simple as a Fourier transform, though part of it is a Fourier transform. But VLBI does that for us for free. Um, but it's a repackaging of all the geometry of um, of the black hole. It's kind of like, if you're in a department store mirror, one of those things with two mirrors on the side, and you look just at the first image, you can say, okay, there's a mirror there. Um, and you can see yourself and you can decide whether you like the new shirt or not. But if you look at the whole successive images, um, and you look at the ratios of those images, you can reconstruct completely the geometry of the mirror. And if I go or if you go, it might be that the shirt looks better on you than on me, and we won't be able to determine uh, that much about uh, from the first image. But if we both go in and we ask the question, what is the geometry of the mirror? We'll come back with exactly the same answer. So it's really striking how all those many parameters that go into the GRMHD simulation of these images completely factor out in these ratios between the successive rings. And so this is a way to really see the curvature of space-time that we've never had anything like before. I mean, Eddington saw a small deviation. Most of what we've here, okay, this is incredible. I love this picture, but still, um, it leaves me it leaves me wanting more, and I think we can get it.
Okay, maybe last question to Peter.
My question is actually builds on these other ones. It's quite related. Andy, what would convince you that we had confirmed conformal symmetry? Do we need to have, n equals 3 over n equals 2, n equals 2 over n equals 1, n equals 1 over n equals 0? Or would something short of that convince you? I mean, I know there are theoretical reasons for deep theoretical reasons built into the general relativity, but in terms of experimental confirmation, what would it take to make the case that we had experimentally given powerful support to conformal symmetry?
I think, yeah, we might. I think to really be sure of conformal symmetry, we'd need to get to n equals 2. And yeah, it depends exactly what we saw. There are different ways you could do it, but of course, one of the really cool things is that the polarization is Michael and Alex and and Mina saw it in a paper. The polarization flips between six successive rings, and seeing that would be, I think, very persuasive if you could see that just in the ratio between um, n equals 1 and n equals 2. Um, and but sort of the simplest answer to the question is if you could see that the um, ratio of the net luminosity at a given angle, um, what between n equals 1 and n equals 2 was the same as the ratio but between n equals 2 and n equals 3. Um, and it was the right number, you know.
What
There's a
about
number.
ring thickness ratios?
I think thickness ratios. Yeah, thickness ratios would be persuasive too. Yeah.
I think
Isn't
we're
the
gonna have
net
to.
luminosity easier to see than the thickness though? That's probably a little harder. I'm not sure.
Thank you, Andy. Great talk.
Thank you all.
Yeah. Thank you so much, Andy.